Okay, so this is going to be the last part, final section of going over the practice exam 3 from fall of 2021, right? So which one is it? Yes, fall 2021. All right, so I made videos on these 3 sections. Now we're going to do this last one. So in this last one, I think something I'm gonna make a note of is that I can tell, based off of what the professor talked about in class, especially the last time, that so when she wrote this test here a couple years ago, she said that, she had done different stuff with different classes at different points. So at this point, they didn't know that when you use the KOH and you remove something, that it doesn't just remove it and make a double bond right where it was removed. KOH specific, if it's at the end, like this is at the end, it'll get taken away and actually get put further in. But the reason why I feel she's definitely going to give us the NH, what is it, 2 over the NH3 is because this is specifically the removal reaction you use when you're removing something at the very end terminal, like a last carbon, like this carbon right here. To keep whatever bond you're going to form, like the double bond, to keep it at the end, you have to use this one. And that's also the example she wrote on the board and said Wednesday during the last lab. So either, pretending that this is actually here for these scenarios, I will, it'll make more sense when I do it. Watch. Let me draw this. So first of all, right, this is clearly fill in the box. But what you need to do, what you need to have memorized on your own is what these different things do at the arrows, not that. So specifically when you see KOH, which acts the same as the NaNH2 over NH3, except for when the carbon's at the end, is that in this scenario, I redrew this cyclopentane, right? And then, you know what, let me color code it. So the cyclopentane, right, is here. Then we're gonna have this substituent coming off, right? And then this chlorine. That chlorine actually is going to connect with the potassium. You see it here. That each time you see a plus, well, when it happens, it's just giving you the byproducts, which can be a hint that this took the chlorine, then this OH took a hydrogen. So 2 things were taken and created a double bond. So what do we have? We have 1, 2. 1, 2. This chlorine was taken, so the bond was taken, not the carbon here, right? So it created a double bond. That's actually not supposed to happen with KOH. That's supposed to happen with NaNH2. So she said she taught a class where she hadn't gotten to that fact yet and they hadn't learned this, so she just still had it to where it would create the double bond at the end with this. But we're technically supposed to know that KOH removes it, but would actually create the double bond right there. It would move inwards because it doesn't stay terminal. the only way to get it to stay terminal is actually through this NaNH2 over the NH3. That would take this and remove the Cl and do that. I hope this makes sense. So the point is that we're supposed to know that KOH, if it's taking something away at the very end terminally, that it won't create the double bond right where it took it away, that it'll move inwards to be more stable. So it would actually look like this. And that if we want the thing to be removed and for the double bond to stay at the end, we have to use NaNH2. And I think of like N stays at the end. So I think she's just simply going to put this here. She's not going to give us this and expect us to do this. Because like she said, we're supposed to know. But we're going to act like we don't know. And that this is supposed to go at the end. And you'll see, because I did this in advance, and you see that if you do it correctly, you can't actually like move on past a certain point. But if you do it quote unquote incorrectly, like this, you can. Again, I know I'm overcomplicating this, hopefully not, but just act like this is here, because we're supposed to do it as if it were. So, the double bond gets created and stays at the end. That is exactly what's supposed to happen with this. Stay at the end. Now, 500 years later, what do? You're supposed to now look at this and apply this reaction to this. So, let me just redraw it. But what are we doing now? Super important. What are we doing? This is adding 2 chlorines. That little 2 can't get ignored, because what this really means is that there's 2 chlorines getting added. And just 2 chlorines. Well, a good rule to always know and remember is that 1 bond equals 2 atoms. Right? 1 bond represents basically 2 electrons. It's because each electron comes from a different atom. So here is an atom, here's another. I'm just using carbon for this one. So the point is that if we add 2 chlorines, then we're using an entire bond to do that. And so it goes away because you're using it. And it's just good to write them going opposite directions, because they're big, bulky things. They're not going to be right there. They'd be interfering with each other too much. So they go in opposite directions. Right, so we used that 1 bond, that double bond that was created right here, right, to simply use half of the bond for this chlorine and the other half for that one. Hope you're following so far. Now, again, what we're going to do is we're going to take this and we're going to put this, because I promise you I'm not leading you astray with this. We're going to act like this is actually here. And right, she had 2. That's super important to realize and look out for. What does that mean? Basically means this NaNH2 twice. So it literally means NaNH2 and NaNH2. And that's important because what you're going to see is that one of the NAs takes one of the chlorines, and the other Na takes the other chlorine. Okay? But not only that, one of the NHs takes a hydrogen that we don't see, and the other NH is going to take another hydrogen we don't see. So it's actually taking 4 things. 2 things we see and 2 hydrogens we don't see, because never show hydrogens. That's why here, and this is written because of that, this would be plus 2 NaCl plus 2 H2, NH3. Right, because the 2 turned to a 3 because we added a hydrogen to that one. We added a hydrogen to that one, so it made it NH3. It made this one NH3. So we got 2 of those, 2 of the NH3s right there. So what does that do? Well, we still have this cyclopentane, and we still have this, basically it's an ethyl group, like 1, 2 carbons, right? 1, 2, 1, 2. And we removed a hydrogen. Oh, sorry. Yep. We removed a hydrogen here and a chlorine. And remember, 1 bond equals 2 atoms or elements, whatever. What does that mean? If we take 2 things away, we're going to get a new bond. If we take 4 things away, we're going to get 2 bonds, because 1, 2, 3, 4, right? 1, 2, it's a bond, 2 things. 1, 2, 3, 4, double bond, 4 things. So we took 2 things away. Up here, 2 things away down here. A chlorine and a hydrogen, a chlorine and a hydrogen. So this bond can represent the chlorine and the hydrogen on the top, and then this one can represent the chlorine and the hydrogen on the bottom. That's why you went from this like single bond thing with only 2 chlorines you saw to suddenly a triple bond, because each bond represents 2 electrons or 2 elements. So now what do we do? Working with this. So we got this far. All right. So when you see this, right, and you just see the ether or THF, right? It could be ether or THF, and that's it. It's Markovnikov. Markovnikov means you put hydrogens where there are the most amount of hydrogens. Okay. Now, what does that mean? Do you realize right here that we're dealing actually with 2 atoms or 2 elements? And the thing that should never talked about that's actually the case is, so you know how we just are learning substitution and elimination, never talked about, explicitly kind of really just compared what we're doing, is that this is addition. Well, except for when I'm eliminating, right, removing. But you see, this was addition, this is addition, this is addition. What that means is we're adding. We're simply adding, not replacing, not eliminating, we're adding things. And remember, 1 bond equals 2 elements. I have 2 elements. I have a hydrogen and I have a bromine. So let me draw this basic part, right? Because we're always working at the triple or the double bond. Because when you have a double bond or you have a triple bond, you have extra electrons that can be shared or used to do stuff. So that's why you don't have to randomly memorize that like something's going to be added here, 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 here. It's always at where there's a double or a triple bond. So we have 2 elements and we're going to add them to this. So that means we're going to use one of these bonds, right? Because 1 bond is 2 elements. So we got 2 elements, so we're going to use 1 bond. So let's just not even write that one. But we are going to write this one because we're not using it. Okay? Now, though, let's back up to the Markovnikov, right? Because you're like, well, where do I put the hydrogen? Where do I put the bromine? Because really, I mean, you could do either. But no, you don't. You can't, because this guy figured out that that's not how it happens. So I'm just going to write Mark. Markovnikov said hydrogens basically go and hang out with hydrogens. Okay, so you have to know, where are their hydrogens already with what you're working with, right? And we're not working with this yet. I just drew that in advance. We're still only looking at this, right? We're going to take this and run this through this reaction. So how many carbons are there? Remember, always at the end is a carbon, and at every bend. So we have a carbon right here. We have a carbon right here. Or we have a carbon here. Right, we got, that's a carbon, blah, blah, blah. It's all the red. Carbon, carbon, carbon. Right, at every bend and end. But again, we only care about where there's double and triple bonds. At this carbon, remember, carbon likes to have 4 things around it in different configurations. Like that singly, or carbon triply, or doubly. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So how many does this have? 1, 2, 3. That means that there is something not being shown. And there is. There is a hydrogen right here that's not being shown. That's supposed to be assumed. Now what about this one? We got 1, 2, 3, 4, right? 1, 2, 3, 4. It does not have anything else. It has its 4 connections, 3 of them to this carbon, 1 of them to this carbon. There's nothing else there. There's nothing else assumed. So there's no hydrogen there. So you're not going to add a hydrogen here because there's no hydrogen. Markovnikov. This is a Markovnikov reaction. So is this one. Says, if you're going to add a hydrogen, which we have right here, you're going to add it where there's most hydrogens, and this is the only carbon that has any hydrogens, so it's also the one with the most. So what does that mean? That means now we know exactly where to put the hydrogen. Where are we going to put this hydrogen? We're going to put it right here, but we don't have to show that, and we don't show it, we don't write it. Where are we going to put this bromine? Well, we're going to put it at the other part, which we would show, and we do show, because now this carbon still has its 1, 2, 3, 4, right? Okay. So then, this is actually the exact same thing. The only thing that's different is that it's chlorine and not bromine, but they're both halogens, and this is also Markovnikov. So we're going to take this and run it through that. And we know we got to put the hydrogens where there's most hydrogens. And there's no hydrogens at this carbon, because we have a bromine doubly bond to a carbon and singly bond to that carbon. So it has 1, 2, 3, 4. And we still have 2 elements. So the hydrogen's going to go where there's hydrogens, which is there. And the chlorine's going to go here. And this double bond, right, disappears because it was used by this chlorine and this hydrogen you don't see. All right. Now, to do this reaction, we have to use this. We have to use what's in this box to run it through this reaction. Here is nice, and she gives you a hint that there's 2 things that are going to be created. And I noticed that this one thing, she makes this box smaller, and you'll see why in a second. So the main thing, this is the ozonolysis. What does that mean? Ozone, the O3, and a zinc with hydronia. What this does is different things depending on what you're starting with. Well, what are we starting with? And you remember, just look at the bonds. we're starting with a triple bond. So let me just rewrite it. Starting with a triple bond. This is the alkyne. When you run a triple bond through ozonolysis, what you get is it splits it, right? It's gonna split right down the middle where that bond is. Let me make this bigger. That's the lysis part of it, like it breaks it. It lyses it open. Okay, and then what happens? Well, this is why and when it's super important to basically count carbons and know where the carbons are, right? There's this end that has carbon. Just say carbon 1, especially if you don't have different colors on the TES. Then we have another carbon, right? But where it splits, and especially in these ones where they split, you want to start the numbering back over again because it splits them in half, right? 1, new carbon 1, and then you have these different carbons, and actually it doesn't matter at this point because we're splitting it at the end. Now watch. What happens is when you split something at the end, you don't have anything over here except for a carbon and a hydrogen technically, but it's a carbon. What that always happens in these cases is it creates a carbon dioxide, the CO2, because it's this C right here that's basically by itself and connects with hydrogens and creates a molecule on its own. What happens then is, so now that's gone, and you have here this carbon, right, where it split. Well, that carbon now, let me clean this up. Right, that's all we have at this point is this carbon. Right, this split, so the triple bond is gone anyways. This turned into CO2. Now you still have all of this left right here with that carbon. Well, what you do specifically, and you have to just have memorized, is ozonolysis with triple bonds creates a carboxylic acid. Oh, what's a carboxylic acid? Well, it is, this one's funky to draw. The carbon that's right here already doubly bonded to an oxygen and an OH. So the carboxylic acid of this is right there. That's what gets added. And it gets added to where it split. Right there. For alkynes, for triple bonds. Now, I don't know if she's going to give us, she may not, but if it's a double bond, remember that O3 in zinc does not create carboxylic acid. If you look back, you'll see that it creates ketones and aldehydes. So this without the O is an aldehyde, and then without the OH, it's a ketone. But not trying to confuse you, just trying to remind you that in case she gives it, it's a double bond at this point, this is going to be different. So go look back at that in the reaction mechanisms, like handout sheets where she put them all together. All right. Now, what do we have? So now it's different. It's kind of like a different question. We have this chain that we need to run one time through this reaction and show the result here, and then one time through this one and show the result here. Okay. Well, how long is this chain? 1, 2, 3, 4, 5, 6, 7. All right, it's 7. Now you need to know and have memorized that this Li over NH3 will make something that is a triple bond into just a double bond and will make it trans. And it's actually already trans. So trans as in things are staggered, right? Where it would kind of like, it would give you an E configuration, or the priorities are on different sides, or they'd be pointing in different directions. And so this like normal chain is that. So actually we don't have to switch anything with the chain, we just have to take away one of the bonds, because it turns 3 bonds into 2 bonds. So I'm going to do the 1, 2, 3, 4, 5, 6, 7, and then where is that? 1, 2, 3, 4. 1, 2, 3, 4. So we got the double bond, and at 1, 2, 3 we got that still. It didn't touch that, so it's almost identical, just double bond as opposed to a triple bond. This one, Lindlar's catalyst always makes things cis. So I think Lindlar's catalyst, the cis, meaning it makes things on the same side. So you're going to have to kind of do this ZE thing priority and try to figure out if this already, in terms of the priority at these carbons, is cis. So let's draw this. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 3, 4, 5, 6, 7. Okay. So we know that they actually both take away a triple bond and make a double bond. We still have this bromine there. Now what happens is we have to think, there's a carbon here, and there's a carbon here. And this carbon has how many connections right now? 1, 2, 3, but it needs 4. So that means that there's really a hydrogen there. This carbon, 1, 2, 3, so it needs 4, so there's really a hydrogen there. Okay. Now that means, right, I'm gonna do like the pretend, like, oh, I'm splitting it, and I'm gonna check and see carbon by carbon. This carbon, what is it connected to directly? On this side, it's connected to a hydrogen and another carbon. Oh, whatever. What about this carbon? This carbon is connected to a hydrogen and another carbon. Okay. So looking back just over here, I see this carbon is a hydrogen and a carbon. Well, carbon takes priority. So that means that the priority for this carbon is that one. So it's down here. Now when I look at this carbon, what the heck did I write there? When I look at this carbon that's attached to a hydrogen and another carbon here, this carbon is what? The priority, because carbon or hydrogen, carbon always wins. It's heavier, so that's priority. So this carbon of the double bond has its priority going that direction. This one has its priority going that direction. That's E right now. But Lindlar's catalyst makes cis, which means same side, which means something has got to get changed so that this and this are both here or both here so that they're on the same side. Well, you just have to think, what's the easier way to flip stuff around? Probably just to move this and swing it down over here. So let me rewrite it in here. 1, 2, 3, 4. Oh. And it can really help to just number so you don't need to unnecessarily lose your place with stuff. So it's like 1, 2, 3, 4, 5, 6. And I want to bring this down here so that this carbon is pointing down here. Well, how am I going to do that? well, let me see where the bond is. So 1, 2, 3, 4. It's at 4. So I got 1, 2, 3, 4. So that double bond is right here. That means let me move this whole portion 6, 7 down. So 1, 2, 3, 4, 5, 6. Let me see. 1, 2, 3, 4, 5, 6. And then, yeah, whatever. 7. So what happened was we still have this portion right here. And then I just took this and put it down there and swung it this way as opposed to this way, because that's gonna be like too much whatever. All right, so what does that even mean at this point? Count your carbons, make sure you didn't lose anything in the process. 1, 2, 3, 4, 5, 6, 7. Yeah, so I have everything accounted for. Now these will both have their priority going in the same direction. Right? Yeah. Okay. I'm tired. I bet we all are. This is a lot. All right, what do we got left? Okay, we just got these 3 ones. So it's not as crazy as it looks. All right, let me redraw this and just bring it over. Okay. So when I look at this, I think of basically what I would have had to have memorized from the reaction sheet is, what does this do? So when you have alkynes, so a triple bond, and you see this mercury, whatever, sulfate, it is actually a hydration. So it's actually adding an OH, but it doesn't do it like it did for double bonds. So for triple bonds, this does something kind of weird and funky. You just have to memorize, as it actually adds an oxygen double bonded, and specifically to the quote unquote internal part, right? So you have a triple bond, and you have here would be terminal because there's terminates here, it's at the end, there's nothing else after it. Here it would be internal because it is connected to the rest of the molecule. So the HgSO4, it will put that internally. So it removes the triple bond and plugs that in right there. That's what you have to remember specifically with this. And I always think, like, I see the HGS, right? I think hugs the HGS. I think that, like, how it hugs it, like, from the inside, it brings it in, like, hugs this oxygen triple bond in here. It's Markovnikov, because actually it's like, oh, the hydrogen connects here, the oxygen connects here, but it double bond connects because it's a triple bond, whatever. The thing that is important with this is because this is its opposite. This is the anti-Markovnikov one. This is the situation where, let me just bring this over. You have this triple bond at the end, and you're going to add also an oxygen double bond, but not internally, terminally, so at the end. So it takes away the triple bond, it puts this oxygen double bond and adds an H to it. The way I remember this in particular is that I think about how you add an H to the butt. I was thinking like, oh, it's at the end. These two are related in that they're considered hydration, where it's technically like oxygen, it's like hydrogens and oxygen getting added. Well, this is anti-Markovnikov, so apparently though it added whatever stuff over here, but it's basically the opposite of this. So it actually adds the oxygen double bonded terminally as opposed to internally, where it normally would want to have the oxygen double bonded further in. So it does its opposite. All right, and you're always working at the carbons in between the triple bonds or the double bonds. Now, a very, very last thing, last one. This is where it's so important to either color code and or count your carbons. So I'm gonna put this in here. I'm gonna say carbon, 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 right? And not only that, but this little bromine, you see, is gonna get removed. So this Na, this positive ion, is going to take this negative ion and combine there. And then this part, NH2, is going to take a hydrogen and turn into NH3. And the reason why it's doing that is because it's going to add this whole thing onto here. So we just got to redraw that from over here. And we got to realize that this reaction does not remove this triple bond. It doesn't affect it actually at all. What happens is simply that this whole portion gets added onto here. But you need to really make sure you don't get rid of or add any unnecessary carbons. So like carbon, 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 right? So we got carbon, 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 those 4 carbons, right? It's in here, it's still here. They don't go anywhere, neither does the triple bond. Here, we're gonna have 1, 2, 3, 4. Well, know that this comes off, right? You see, it connected with that connected with that, turned into that. It's gonna come off, and right here that's where you're gonna connect, right? Is where this goes away. So there's this like funky little in between where you need to actually elongate this out to then connect this part. So see, this is the part where the bromine disappears. So it's the part where the molecule connects to this bigger one. So what am I gonna have? I'm gonna bring it out. I'm gonna have 1, 2, 3, 4. I have 1, 2, 3, 4. Right? 1, 2, 3, 4. Or you say 1, 2, 3, 4. 1, 2, 3, 4. And then we're at 1, 2. There's this thing down here. So at 1, 2, I just pop it upwards. It doesn't matter, up or down. And then you got to make sure you, again, have everything. So it connects here. We got carbon 1, 2, 3, 4. I got 1, 2, 3, 4. Then at 2, 1, 2, I have this. 1, 2, I have that. And, yep, so there, you can see this was this little part here, and then the rest of the molecule just gets added. So nothing got taken away, nothing got removed from what's drawn here, like physically, like none of these carbons go away. They just get smashed together. And let me even do it. Carbon 1, carbon 2, carbon 3, carbon 4. Carbon 1, carbon 2, carbon 3, carbon 4. Right? Do 1, 2, 3, 4. 1, 2, 3, 4. Right? And then you have everything. And that's exactly what you want to make sure, because that's basically where it's the absolute easiest to mess up. Now, before I finish this video, let me let me look at my little notes situation, make sure 1, 2, 3, 4, 1, 2, 3, 4. Yeah. All right, 1, 2, 3. Yeah, okay. It just looks funky the way I wrote it. And it's fine how we write it if it's a little messy, as long as all the carbons are there. That's the big thing, is you're always showing the carbons aren't disappearing. Even in here, they didn't disappear. You had 1, 2, 3. Now it's 1, 2, and the third one is right there. The CO2 always gets created when you split something at the end, and when you hit it at the end, and there's only 1 carbon right there. I hope all this helped. I know it's really convoluted, a little overkill, but whatever. If there's anything wonky or weird, definitely message me or whatever, leave a comment or something, let me know. And yeah, really, I hope it helped. I mean, it helps me obviously go over this, but hopefully you got something out of it.